A few interesting applications of the Bernoulli equation um, related to the concepts that I talked about before is that if you increase the velocity, then the pressure decreases. It'll be difficult to see on this video, but you can try this yourself. If you have a piece of paper, you just have a sheet of paper, and you're holding your sheet of paper like here, and then if you blow over the top of the sheet of paper, you're going to increase the velocity of the air above the paper, which decreases the pressure above the paper, and therefore there's more pressure on the underside of the paper than there is on the top side of the paper, and the paper will actually rise up. So you can try that right now. Just hold up a piece of paper and hold it hold it up to your mouth and blow over the top of it, and you'll see that it will kind of rise up. That's kind of neat. The same sort of idea can cause, if you've got a house and there are really strong winds, if the wind is strong enough, this wind will blow and it'll decrease the pressure above the house, and the roof can actually blow off of a house if the wind is strong enough. Another thing is like if you're in a river, according to the continuity equation, the same amount of volume has to flow by given points at different times. And so like the water on the inside of this curve has less distance to travel than the water on the outside of this curve. So if you're in a river, the place where the water is moving the fastest is actually around the outside of the curve. So that's just a couple of interesting applications of the Bernoulli equation. Now, in all of this, we have not taken into account friction in any sense. But in reality, there is friction between the fluid and the walls of whatever pipe this is. The volume flow rate past a given point, the volume per time is equal to, a lot of things go into this. There's the pressure difference, which is basically the force, so that's important, times pi times the radius to the fourth over 8 times eta times L. This is the Greek letter eta. It's kind of like a long N with this little tail. L is the length of the pipe or whatever it is. This r to the fourth dependence, this takes into account friction, whereas our Bernoulli equation did not. And this becomes important when the radius is small. So if you have a smaller, like blood vessels and whatnot are pretty small. So if the vessel contracts even a little bit, you wind up at much greater risk of a heart attack because, in r to the fourth dependency, if you change r a little bit, it decreases just a little bit, then your volume flow rate decreases dramatically, and you have much less blood flowing. So that's why even if a blood vessel contracts or artery contracts a small amount, you can have you have a much greater risk of heart attack or stroke or things like that. We're not going to do a lot with this except to eta is the viscosity, is the coefficient of viscosity, which is like the term for liquid friction. We're not going to do a lot with this except to say, like, to half the volume flow rate, what has to happen, and if you want to, like, half the flow rate, then basically you're saying 1/2 is equal to your percent change in r, whatever that is, times to the fourth, right? And so basically, you just take a fourth root, and then you can figure out by what fraction the radius of your blood vessel or whatever it is changed. So that's as far as we're going to go with that. But I just want you to know, like, this is something that engineers and whatnot do have to take into account, that there is this friction between their pipe or whatever and the fluid inside it.